Increase or decrease in temperature due to heat being supplied or extracted from an object changes the phase of the object. This was the lesson we learned from last video. From solid to liquid to gas, as the phase changes, the volume it occupies also changes. 1 kilogram of ice can easily be stored inside a typical refrigerator. 1 kilogram of steam takes a lot of space. Generally, when an object is heated up, it is expanded. Even when an object keeps its phase, it will still expand when it is being heated. Of course, there are always exceptions or anomalies in nature. Probably some of you might have heard that when ice is heated, its volume will decrease until it reaches 4 degrees Celsius. Of course, by then it has already melted into water, before it starts to expand as expected. But typical object expands when it is heated. This lecture video is going to explore this phenomena collectively known as thermal expansion. Furthermore, in this lecture we will only focus on thermal expansion in a solid material. We will not talk about thermal expansion in a liquid in this course, but we will discuss thermal expansion in gas in the next chapter. So let us start with a solid rod of length L. The length of the rod is way more significant than its thickness, that we can aesthetically treat this solid rod as one-dimensional object or a line. This is also to say that when the rod is heated, it will expand mostly along the length of the rod. The new length is denoted by L prime. The expanded length is denoted by delta L. Hence, we have the further relation between L, L prime, and delta L, which needs not further explanation. The question is, what is delta L? Well, we have an empirical equation to compute delta L, which is given by alpha times L times delta T. The physical meaning behind the equation is that delta L will depend first on the original length of the rod. A longer rod will expand more. Second, on the increase in temperature, delta T. The hotter the rod, the more it will expand. But do keep in mind that there is a limit to this, because we already learned in the last lecture video that if we continue heating up the rod, its phase may change completely, and this equation is no longer making any sense. Furthermore, delta T could assume negative value. That is when the rod cools down. Negative delta T leads to negative delta L, which means that the rod contracts when it cools down. And the third and last thing the expanded length delta L depends on is the coefficient of linear expansion, which is denoted by alpha. Just like heat capacity or latent heat, coefficient of linear expansion is a constant characteristic to the material the rod is made of. For instance, if you look at this table of coefficient of linear expansion, aluminium has higher coefficient than steel does. So when heated up by the same rate, aluminium will expand more than steel. This is what alpha physically means. Now, how relevant is this equation to us? Perhaps not much. After all, when cooking your favorite Maggi mee, we don't really observe if the saucepan has gained extra centimeter from the heat, do we? Well, the problem is, alpha is a small number, power of -5. As a matter of fact, the saucepan does expand under heat, but our naked eye won't be able to notice that tiny minuscule expansion. It is not so if you are dealing with civil engineering structure. The expansion of NUS U-Town link bridge from the temperature difference between night and day can amount to few centimeters, and that's why civil engineers have to put down this gap to accommodate this expansion. Failure to do so may result in disasters such as this classic example of the railway went wrong. Steel is more elastic than concrete. When there is no room for expansion, steel will bend. Concrete is brittle. For concrete, it will just crack and crumble. Surely we won't use a bridge which could crumble anytime. Physical object comes in 3 dimensions. When heated up, they will expand in all 3 dimensions. How shall the equation look like in era of volumetric thermal expansion? Well, let us first examine this rectangular plate. I use rectangle as an illustration here, but the idea can easily be applied to any 2-dimensional objects. The rectangular plate has an area A, which is given by L1 times L2. After heating, it is expanded to a larger area A prime. Each dimension or each side of the rectangle will expand independently. Hence, similar to the previous slide, the expanded side of the rectangle is given by L1 prime and L2 prime, who are related to the original side by the following equation. What we are about to go through in the next slide is a derivation on how the expanded area A prime is related to the original area A. So here we go. I will let you go through the algebraic steps on your own. See if you can follow the steps. I hope that should be quite straightforward. If you have any query, I could imagine that would be the omission of the last term in this step to the next. What happened to this last term? Well, to put it simply, we neglect it. And that's why, going from the third to fourth line, instead of using equal sign, we use this curly equal sign, which is to be read as approximately equal. In other words, the fourth line is approximately equal to the third line. Now, mathematical rigor aside, is there any practical reason for doing this? Is this a physically sensible thing to do? Well, if you look at the last term delta L1 times delta L2, it actually refers to the tiny corner of the expanded triangle. Its omission will mean that we are neglecting this tiny corner, which you will not probably notice if I did not zoom in, from the calculation of A prime. The physical reason for doing so is because delta L is typically a very small number, a fraction of the original L. Even a U-turn bridge, which is a few hundred meters long, only expand by a few centimeters at most. Now delta L times delta L will be an even smaller number. It will be negligible as compared to the first three terms, which contain L square and L terms. Thus, for all practical purposes, we can neglect this last term. The consequence is that we are not able to recast the last step in the form very much similar to the equation for linear expansion. A prime is equal to A plus delta A, whereby delta A is beta times A times delta T. Beta assumes 2 times the value of alpha, and it is technically called coefficient of areal expansion. This looks neat, doesn't it? This is another pattern you guys should notice. If you remember the equation for linear thermal expansion, you should easily be able to recall the equation for the areal thermal expansion. And guess how the equation will look like for volumetric thermal expansion? It will have the same format as its linear and areal counterpart, with its coefficient of volumetric expansion gamma assumes 3 times the value of alpha. You may derive this result algebraically yourself in the same way we did with the equation for areal expansion.